welcome to the our webinar series. Let me introduce the webinar series and its objectives. I hope everybody can hear me. Thank you all for joining from different parts of the world. The Critical Transitions in Complex System webinar series is being jointly hosted by IIT Madras in India and Potsdam Institute for Climate Impact Research, aka PIC, in Germany. This webinar series brings together experts from diverse fields such as climate science, neuroscience, fluid mechanics, ecology, etc., and aims to disseminate the state of the art in the prediction of critical transitions in these diverse fields of study. The seminar series takes place every month on the last Monday of the month, so please mark your calendars. Before I introduce the speakers, a few housekeeping notes. I request everyone to turn off their microphones and kindly use the Q&A box in Zoom. You can find the Q&A box at the bottom panel to ask the speaker your questions. You type your questions there and speaker will answer them at the end. We have ample time for that. So with that, let me introduce today's speaker, Professor Balachandran, popularly known as Bala, received his master's in aerospace engineering and PhD in engineering mechanics from Virginia Tech. Before that, he did his undergraduate from IIT Madras, where I am. Currently, he is a distinguished professor and Minta Martin professor at the University of Maryland, where he has been since 1993. As everyone knows, Maryland is like the best place for, or one of the best places for nonlinear dynamics. His research interests include applied physics, applied mechanics, applied mathematics, nonlinear phenomena, dynamics and vibrations, and control. He holds 4 US patents and on Japanese patents, 3 related to fiber optic sensors and 2 related to atomic force microscopy. He has served as the editor of ASME Journal of Computational Nonlinear Dynamics, a contributing editor of the International Journal of Nonlinear Mechanics, and a deputy editor of the AAA Journal. He is a fellow of the ASME and AAA, an honorary fellow of the Royal Aeronautical Society, and an ASA full member, and an IEEE senior member. Today, Professor Bala will speak about, can noise be used to realize the desired dynamics? Sounds really exciting. The floor is all yours, Bala.
Okay. Thank you, Sujit. Good morning, everyone. Good evening, everyone. Good afternoon, everyone, depending on the time zone that you are in. So the talk today, I'll use to share with you some information that we have collected over many years of efforts, where our goal has been to look at what we can do with noise. So that in the talk today, I'll also refer to it as random intervention. I'll also refer to that as a temporal disorder. So in this illustration that you see, what I have here is a set of experiments we started at Maryland, starting in about 2007, 2008, in which we first started with this oscillator, which is a prototype of a duffing oscillator, if you will. So a cantilever beam with a magnet up on the top and another magnet up on the other side. Depending on how the north and south poles are oriented, you could have either an unstable equilibrium position for the beam at the center, or it could get deflected either side to have other 2 equilibrium positions, stable equilibrium positions, if you will. And then moving on, in later studies, we looked at the same thing in a different configuration, where we use a shaker. The black object here is what is called electrodynamic shaker, which we can use to excite the base of the structure. And then the beam here would oscillate transversely to the direction of excitation. And that we pick up using a strain gauge sensor, the strain at the base of the beam. And the magnets again up on the top, and the thing could be used to control the nonlinear interactions between the 2 pairs of magnets. Again, this was another system that we used to not only look at what happens to the structure as we include harmonic excitation along with noise. We also use this to draw some understand what we can do with atomic force microscopy by tailoring the interactions at the pair of magnets. We could have a force function which had a quadratic nature. Moving to the right side, I have here, what I have here is an array of oscillators, where again, here the goal was to excite the system with an input that had both the deterministic component as well as the noise component. And the goal here was to look at energy localization, which would mean one of the oscillators here, the cantilever structure, would pick up the energy. And the goal was to see what noise can be used to play with this localization. In each case, along with each cartoon, I also listed names of students and postdocs who had worked on it. And then in between, we also worked on a flexible structure motivated by drilling operations, where the goal was to look at how to control the backward and forward whirling motions of the rotor at the base using noise, which is input from the top with the rotation speed. We'll come back to this illustration in a bit. And then off late, we moved from a case of linear array of oscillators to one where we have a circular array of oscillators, one of which is shown in this illustration in the middle and the bottom. In terms of collaborations with Professor Hikihara in Kyoto University, Japan, we created a similar setup to this one to look at localization there and experiments independently to verify some of our findings at Maryland. Apart from the students and postdocs, I should also mention the faculty here in Maryland that I work with, Maria Cameroon and Jimmy Orkin. Okay, so the basic question of interest for us has been, for the last 10, 15 years, has been, if we use temporal disorder, which we call use random noise, random intervention, could we use that to realize some desired dynamics of a system of interest? So that, as we go further, I'll elaborate that desired dynamics could either be transition to another attractor, or it could be synchronization, or it could be shifting localization. So those could be different forms in which the response could occur after the addition of noise. So the first case study that I'd like to get into is that of a Duffing oscillator and the physical manifestation of it in mechanical systems, if you will. So the Duffing oscillator, for those who have not been exposed to it before, is basically an oscillator. Of course, I have a damping term in addition to a Duffing head, the inertia term and the stiffness terms. You have a linear stiffness term, the cubic stiffness term. And here I also have an excitation, which is shown out here, a harmonic function. And the potential energy has two wells, with the well in the middle being the peak at the middle being unstable. And that in this illustration of the structure would correspond to the upright position. When the two magnets repel each other, I would have an unstable position right in the upright position. So in this first set of experimental results I'm going to share with you, what I have is essentially the same structure that you saw before with a tip magnet. And on the other side, I have another tip magnet. And we use a fiber optic sensor here to pick up the displacement of the structure. And that is a sensor here. And I have one magnet at the tip of the beam and another one on the other side, which is fixed in position. So here we are close to grazing contact. So this magnet and this one out to the other side, if I play the video for a harmonic excitation, I'm close to each other, but I don't have grazing contact yet. And then what we could do, if I go to the next slide, with a little bit of addition of noise, a weak noise, you could enable grazing contact. Why would this be important? In atomic force microscopy, if you do a tapping mode AFM, as basically when you have a delicate structure and you impact the structure delicately, you like to have grazing contact so that you don't damage the structure. So from this macroscopic experiments that we do, we could learn at what frequencies we could have grazing contact, and then use the same in experiments with an AFM cantilever. And that's something we have tried, and it does seem successful. So close to grazing contact is usually a period doubling bifurcation, which uses a clue that we have had grazing contact when you're in that range. Moving to another reincarnation of the Duffing oscillator, in this case, again, a structure with a pair of magnets, and with the base of the structure being excited by using a shaker. So in this case, what we did is we have the magnets are positioned, so I have a softening oscillator. So in the deterministic case, if I were to plot the excitation frequency on the x-axis and amplitude on the y-axis, as we decrease the frequency, you'll see that you'll go up on the upper branch. Sorry. You go up on the upper branch before jumping down. And if you reverse your frequency sweep, you'll go up before you jump up to the upper branch and come down. So in the experiments that Dr. Vipin Agarwal did, he's also in the audience today. He's a faculty member at the University of Memphis. We started at 21.1 hertz, which is somewhere right around here. With the noise intensity being 0 in this case, we have purely a harmonic motion, not harmonic, periodic motion. The Poincare section being 1 dot. And as the frequency is decreased for the same excitation level, we end up with the chaotic motion, which is exemplified by the strange attractor, the Poincare section, as well as the fractal structure that you see in the state space plot. At this instance, at this parameter values, if you were to add some noise, which is about 2 units, that's the intensity of the noise that we use in experiments. This chaotic motion that we have is suppressed, and the response moves sort of like a point cloud or to a fixed point that we had in the deterministic case. So in this case, if I were to play the video for you, so essentially, I started from a chaotic motion and then added noise to the system. And then I ended up at a fixed point. The motions ended up at close to a fixed point that I had in the deterministic case. So this is one influence of noise that I've illustrated where we've added a random intervention, that is the random noise, and moved the system from an aperiodic motion to more or less an equilibrium state, if you will, in the response state. So moving to another example, in this case, what we have is a case where you have chaotic motions initially, and then as we move forward after a random intervention, we go to periodic motion. And so in terms of the noise that we have in the system, the noise is turned off initially when the chaotic motion occurs. And then right around this region in the experiments, we turn the noise on. And then after the noise is turned on, we get shifted to a periodic motion. And that corresponds to the system that you see out here, where the parameters that we have are also identified through experiments that we do. So if I were to go a little bit into it further, in the deterministic case, that is without the noise, the system has a chaotic attractor which coexists along with the periodic attractor, whose basin is shown in yellow, and the purple corresponds to a chaotic attractor. And so basically, when I'm in a chaotic state, I'm in this purple region. When I'm in the periodic state, I'm in this yellow region. The corresponding time histories is what you see on the right side. The chaotic time history on the bottom, and insert C, and insert B is a periodic time history. Question now is, how do I go from the chaotic state to the periodic state, or can I do that with the intervention with the random intervention? So the system is fascinating in the sense, on the basin boundary of the chaotic attractor, I have a saddle point or a saddle limit cycle. So essentially, the stable manifold of the saddle point overlap coincides, forms one of the basin boundaries of the chaotic attractor, and also another basin boundary of the periodic attractor. And so the goal would be to, with the addition of noise, is to move the system towards the saddle point and escape through the saddle point to the periodic attractor. And so that's what happens in the numerical results. The points in red that you see here is where, with the addition of noise, we move along the stable manifold of the saddle point. And then with the addition of noise, you move away from the saddle point and hit the periodic attractor. And right in the bottom, these are experiments that Vipin did. And so again, in the experiment, we start at point P0 initially. After addition of noise, we move to P3, P1, then P2. And then these are the intersection of the point gray section. And then we move along, they escape along the unstable manifold to the periodic attractor. So in this case, with a random intervention, we've gone from a chaotic state to a periodic state. And the structure of the system, namely the unstable solution that we had, the stable and unstable manifolds of that system helps us in moving the system from a chaotic state to a periodic state. So my colleague Jim York likes to call it a noise-induced crisis. Jim likes to coin phrases of different phenomena that he sees, and this one he was keen on calling it noise-induced crisis. Of course, when you deal with noise, the color of noise also makes a difference. Just a quick snapshot of what would happen in a case where you had a large amplitude attractor, which is the branch up on the top, the low amplitude attractor, which is the one on the bottom. Again, the same physical system as you'd seen before, basically a cantilever structure with a pair of magnets, and the shaker which excites the base of the system. Again, depending on the color of noise, it turns out with pink noise, we transition from one attractor to another much quicker than what we had in the other cases. So one could make these violent plots wherein you look at the escape time with the probability of it depending on the number of trials that you do. The black is the mean and the red is the median. And in this particular graph, if I draw your attention to the case of pink noise, the escape is much quicker than we had with white noise or a band-limited white noise in this case. So moving on to another set of studies that we did was with oscillator networks. So in this case, the system of interest was essentially pairs of piezoelectric cantilevers. So basically, this silicon nitride cantilever had a PZT actuator at the bottom, had a long cantilever, which we call the A type, and a short cantilever, which we call the B type. They're all coupled to the base. We had 100 oscillators. So if I pull out one cell from it, it had one long cantilever oscillator and another short cantilever oscillator. We have damping, the usual linear cubic stiffness terms, and I also have coupling terms between the oscillators, which you see here with the K sub I and K4I being the coefficients. On the far right, I have the base excitation, in this case, an acceleration. So in this system, if one were to plot the time on the x-axis, the oscillator location on the y-axis, and plot the amplitude of the oscillator as you ramp up the frequency above the first natural frequency, and then you level it off, you could have what are called the pinned ILMs, that is intrinsic localized modes, which I'll come to in a bit, where the energy gets localized and stays as time evolves. There are also sites where the energy pretty much dies out. So the question for us is, could we control localizations like this by introducing noise into the system? So to give a little bit more structure to the intrinsic localized mode that I discussed before, what we have here is a symmetric ILM, basically about the position of 0. On either side, I have a symmetric distribution in terms of the amplitude. Here I've shown 8 oscillators on either side of the one in the middle. So in the system that we have at hand, we have hundreds of oscillators. So you could take your symmetry arguments and break it down to 50 oscillators. And with the 50, you could work around and capture the ILM on one side, as we see in this figure. So in this case, our early foray into this was Euler-Maruyama simulations that we did. So here again, I have the same case illustrated with a little bit more detail. 100 oscillators up on the x-axis or the y-axis, and you have the time plotted on the y-axis. And as the system is excited, there's no noise in this case. It's all deterministic. I have initially localization at about oscillator 12, which dies out as I go up, and oscillator about 60. The energy stays localized for some time and continues beyond as well. In this case, then, if I add noise, as you see in the cartoon on the right side, this is work that was done by Subbu Ramakrishnan, who's now a faculty member at Dayton, Ohio. The localization dies out, and pretty much with noise, what is shown in this case is I can suppress an interlocalized pole. So later on, what we did is we extended the study where we had two different cantilevers to cases where you have identical oscillators array. So it's basically in this case, I have a couple duffing oscillators, if you will. And then in this case, when the coupling energy that is with the noise is 0, I do have localizations at two different regions, two different positions. And with the addition of noise, I introduce a new localization in this case. That's on the oscillator number 5. So again, this is an illustration of with the deterministic case, when I take the excitation frequency, ramp it up to a value which is just about the first natural frequency and hold it constant there. The system gets localized and has a distribution in this form. And then with the addition of noise, we end up with another response state where you can see that you have localization. Okay. So basically, we also tried out the Fokker-Planck formalism, where we go from a deterministic PD to see the evolution of the probability densities and do the method of moments and get infinite set of ODEs, which we truncate to get a finite set of ODEs. And then you could look at the average dynamics as well, and they confirm what we saw previously in our simulations. So this is an experiment that we did at Maryland, where basically we had an array of 8 oscillators, and the oscillator number 4 is where we had the localization. What I would like to illustrate through the video is after addition of noise, the localization that we have in the middle gets suppressed. So the base of the structure is being excited. Initially it's harmonic, and then through the shaker, we introduce noise into the system, and you'll see the result of what happens after we introduce the noise. So through the introduction of noise, we basically moved the system from a localized state where oscillator number 4 had a high amplitude, relatively speaking, to the other oscillators, to a case where all the oscillators more or less have a low amplitude state. So to verify these findings, we also did experiments up in Kyoto University with Professor Hikihara's group, where I have, again, a set of 8 oscillators, and oscillator number 5 was the one of interest for us. And we had the orientation was a little different in these experiments. We had electromagnets at the bottom, and then permanent magnets at the base of the cantilevers. They were all coupled to the coupling rod. We had springs in our experiments. We had a coupling rod, and we used a magnetic actuator to actuate the system. And that through that, we again did the same experiments as before. The structure of the equations is fairly similar. A linear oscillator term, a damping term, the magnetic force interactions. This is a coupling term, a harmonic excitation plus a noise term. In the experiments that we did, again, we had a softening behavior. So as you move down from the right to the left side, as move down in frequency, at about 33.5, with introduction of noise, we have a jump, and then the localization is suppressed. And then we could also further out somewhere in this region with the noise, we could also move the localization around. The darker regions in these figures correspond to higher amplitudes. So again, this is just experimental confirmation that what we saw before, that is through the introduction of noise, you could suppress localization as well as move it around. And then, so this is another set of studies that we did. In this case, again, an oscillator network. And here our goal is to look at transitions from one response state to another. So in this case, we have 8 oscillators that are configured in a circular array. So this is a system of dihedral symmetry. The coupling in the middle is the ring provides the coupling between the oscillators. Again, at each oscillator, a pair of magnets, one on the cantilever and one in the fixed structure. The other side, and the excitation is provided to the motor up on the top. And this work was done by Lataro Silenti, who got his PhD at Maryland, and Jonathan DeBoer, who's currently a PhD student at Maryland. So this is a case, one example where I supply an excitation through the thing in the top. The energy gets localized in one of the cantilevers that you see, similar to what you saw in the inline array experiments that we did. And so these experiments could also be relevant to where you have bladed discs in cases where you have systems with blades arranged in a circular oscillator. For a case with just 4 beams, we have these are the possible response branches. In this case, each oscillator is softening in character. I have a case with all the 4 labels are H-H, which means each oscillator is in a high amplitude state. This is another case where I have an oscillator where one of them is in a low amplitude state. And then we have other cases as well, where the last one being where all the oscillators in low amplitude state. So you could, by changing the excitation frequency, one could move up the branch, just like what we had seen in some of the earlier cases. And then here, through introduction of noise, transition to the branches below. And again, this is noise-induced transition from a high amplitude state or localized state to a case where you don't have localization. We also develop a machinery for it, and to look at what happens for these transitions. In the case with 5 oscillators, we have 32 attractors, which are illustrated here in these response branches. One could use a combination of large deviation theory and optimal control theory, and then the action plot method to track the escape paths. And from that, when you end up in another attractor, and this is actually published in Chaos. And so this, we've used the same machinery for other systems as well, but the quasi-potential computations are not straightforward. They do require some work, but we have been able to do that in this particular case. Again, these compare well with what we saw in the experiments, although in this case, I have a hardening oscillator compared to what I saw in experiments that you just saw. The next, I'll go to some recent results that we obtained. Again, oscillator network. So here our interest is in synchronization. As I saw that many of the CS seminars have addressed synchronization before, so many of what I'm going to talk about in the next few slides may be familiar to you. It goes all the way from Firefly synchronization to clock synchronization to power grids, as well as human brain, as well as the London Bridge, when people are walking under the gate-led synchronization of the oscillations of the bridge. They've all been commonly described as in the Kuromoto model, which Kuromoto discussed in his book in 1984. So the Kurobato oscillator is a gradient dynamical system. So that is, I can write x dot as minus grad v, where v is a potential function. And so after some approximations, if you focus on the phase, you could say the phase phi dot is a frequency plus some coupling terms. K is a coupling strength. In these systems, it's well known that depending on the coupling strength, you could have a synchronization where the phases all turn out to be the same for all the different oscillators. The question for us was, how do we carry those results forward to mechanical as well as optical systems? So for that, we introduced the Matthew Duffing oscillator paradigm, which basically is a non-gradient system. Most systems that we deal with in mechanical engineering are non-gradient systems. So going from that to the Kurobato oscillator requires some approximations, which may not always be straightforward. In this case, we have a periodic excitation term to the stiffness, which in our setup that we had before could come to the axial motions through the magnets along the beam. And then you have the cubic force in each structure and the coupling terms. And the noise, again, could come to the same mechanism as before. The question for us was to look at limit cycles of the system and examine if by adding noise, we could synchronize the limit cycle motions. So again, each oscillator by itself would have a Duffing term and a Matthew excitation term. And the other terms that we have are the coupling terms between, this is a local couplings between adjacent oscillators. So in the noise-free case, uncoupled limit, you could do a method of averaging and take the fast scale out of the picture, end up with a slow scale, where you have the variation of the amplitudes in the Cartesian form u and v, vary on a slow scale. Then could plot your response curves in the slow scale. So basically, depending on the excitation frequency, I could either have one solution, which is one stable fixed point in the slow scale equations, or one limit cycle. And then if as you vary the frequency, you could end up with 3 fixed points, one unstable, 2 stable fixed points. And if you move further out in you have supercritical Pitford bifurcation, you end up with 5 solutions. And so this is all just with one single cell or a single oscillator. So without noise, if I go to the oscillator array, so I've included the coupling terms now, and I've n oscillators. In our studies, we've gone up to 100 oscillators. Again, you could use a method of averaging to get your average equations or the slow scale equations. And you can look at the number of solutions that the system has grows quite a bit with the number of oscillators that you consider. And again, we are going to look at the case where in the nominal case, you'll have a harmonic excitation, a parametric excitation, whereas omega will be twice your natural frequency of the system, that is 2 omega. So in the case without noise, I have the blue with the stable fixed points. As I change the coupling strength, one could study how the norm of the amplitude in the slow scale changes, and the red are the unstable fixed points that we have. And if I look at it in terms of order parameter, where I basically look at the different phases collectively, when order parameter is 1, that would mean all the oscillators are synchronized. All of them have the same phase. 0.8 would mean most of the oscillators except 1 are synchronized in an array of 10. And then you have 0.6 would mean except 2, the other 8 oscillators are synchronized and so forth. So the question for us was, in a system like this, could I use noise so that way I could stay in a state where all the phases are synchronized? And so without the noise, again, these are different trial numbers, and the oscillator numbers plotted on the x-axis. And as you can see in the case without noise, none of the trials that we did, the phases are all not the same for all of them. In other words, I don't have any synchronization, full synchronization in all the different cases. I do have some partial synchronization or chimera states, but not a full synchronization. With white noise addition, I see that all the phases are synchronized in all the different trials that we did. And if I give a little more detail into the order parameter, the blue one is the result obtained after we add noise to the system, where we basically see that addition of noise does promote synchronization in this case. Without noise, I have the response a little bit scattered all over the place. I probably might have at best partial synchronization, but not a case of full synchronization. To close the talk, one last example is a flexible rotor system. In this case, again, we'll use random noise to move the system to a desired dynamic state. So these studies are motivated by oil well drilling applications, where this is your rotor, which is fairly long. The aspect ratio is similar to that of a human hair. In this case, the twisting of the torsional motion is the same as the bending motion, so which we replicated in an experiment. So if I take a section between these two sections here and I expand it, that's what the experimental setup is. At the end, I have a disk to which we added a mass, includes some eccentricity, and then the outer thing mimics a shell. And I have a camera to pick up the motions of it, and in the experiments, I have a slip ring to measure the response of the flexible rotor and the servo motor up in the top, similar to what you saw in the circular array, to provide an input to the system. So when people are drilling, they would like for this rotor at the base of the bit to be as close to the center as possible. So that way it doesn't make much contact with the outer shell. And then you can do the boring in the direction that you would like to do. So these are illustrations of what happens in the case. The first case in the left, I have rotation in the same direction as my input, and I have forward whirling. In the second case, I have the whirling direction, which is in the opposite direction of my input. It's called backward whirling. The backward whirling case, as you could see, is a little bit more dangerous than what I have in the forward whirling case. And if one were to do a simple model by looking at what happens with contact, without contact, one would follow the black lines from the blue, and the stator is, the one on the top, the rotor is the one in the middle. There's no contact with the stator. When there is contact, I end up with different branches of solutions. One is the backward whirling solution that you just saw in the illustration, and the two solid lines in blue are the forward whirling. So a question for us is, could we use noise to move us from either a backward whirling situation to forward whirling? That was the question to which we started out with. This is an illustration of experiments that we did where in the motor that you saw up on the top, we had some noise, and we saw we could shift the response from forward whirling to backward whirling, although in practice, this is not what you'd like to have, but at least these experiments are proof that you could do this response transition in the system. We are also able to verify this through simulations. So the model is a lot cleaner than what we had in experiments, where we also had to take the delay effects into account. Nevertheless, what we showed here was one could transition from one response branch, the forward whirling branch, to the backward whirling branch. So in practice, what you'd like to have is you'd like to move away from the backward whirling branch. So in another study that we did, this is work with Dr. Vipin Agarwal, where if I draw your attention to the model that you have right here, phi is your rotor displacement or the angular displacement. So the system could either be in a case where the rotor in the middle rotates in the same direction as your input, omega, and there's no contact, forward whirling without contact, or you could have contact. This is another possible state. Or a third state is with backward whirling, where the rotor is moving in the opposite direction of your input frequency, and then you have contact as well. So in the deterministic case, we started from a case that you see on the forward left at the bottom. So the phi dot, you have a backward whirling state. That's why the lines are facing the left side with respect to time. And then after addition of noise, we have interrupted contact, which is what you see in the middle picture. And then as I go further out in time, I move to a case of forward whirling. And after the noise addition is turned off, I stay pretty much in a forward whirling state. So in this case, you've used a random intervention to move from a state of backward whirling to a state of forward whirling. This is something we haven't verified experimentally yet, but certainly at least this provides us an avenue to explore further. So to summarize what you heard today, so I talked to you about noise influence dynamics in different types of nonlinear oscillators and the transitions from one attractor to another, destruction of localization and creation of energy localization, also creation of full synchronization, if you will. And then in current work, we're doing further experiments with the circular oscillator array and looking at the connection with the chromometer model. So far in the studies today, I've pretty much looked at cases where you just have temporal disorder. A question of interest for us is also what happens when you have parameter disorder. In another system, we're also looking at the Fitzhugh-Nagama model. This is collaboration with Elena Rybalova from Saratov University, where we're looking at a slow scale and a fast scale equation and looking at the addition of noise. And by playing with the R term, we can check the number of neighbors that are coupled. We're looking at how we could use noise in this case to create different types of desynchronized as well as fully synchronized states. And with that, I come to a close. So thank you for your attention. I'll be open to any questions or comments that you may have. Thank you.
Thank you, Bala, for this wonderful talk. I request the audience to type the questions in the Q&A box. And in the meantime, perhaps the panelists can ask the questions till the questions come up on the Q&A box. Jürgen, go ahead.
Yeah, thank you very much, Bala. Really highly impressive talk. I'm really very excited. Let me ask, you mentioned that you could jump from one attractor to another due to noise. I understand when you have a multi-stable solution, can you really have then jumps one after the other in some series and get also some order of jumping, let me say, jumping between the different attractors? Have you seen such things also?
Yeah. I think in one example that I showed today, actually, we did do that. I think if I let me come back to this one. Yeah, this one here, right here. So where we started with a case where we had all beams were in a high amplitude state. And then we added noise to bring it down to one attractor where just one oscillator was in a high amplitude state. And then another additional noise, we brought them all to a low amplitude state. So in each case, at least in the system that we have, the escape seems to happen through a one-dimensional manifold. There's a saddle point, a saddle limit cycle, and we're escaping through the unstable manifold of the saddle limit cycle. So basically, the noise was taking us through the stable manifold, through the saddle point, and then we escaped to the unstable manifold. That seems to be the mechanism that we've seen so far, at least in these experiments.
But I mean also with the Kuramoto, you had there these clusters. Can you show please again?
Yeah. So this one that we showed was for a non-gradient system, this one.
yeah, here you have these different solutions, and could you jump then among the different clusters with the same amount of noise, I mean?
That we haven't done that yet. I think that we have not studied yet, not in this system. We haven't figured that out yet. I think this would also require some clever way to add the noise to move the system. We haven't done that.
Okay, okay.
Yeah.
Thank you. Thank you.
Welcome.
Thank you, Argan.
Yeah.
The other questions?
Yeah. It's a very beautiful talk, Professor Balachandran. It is lots of work that you have reported, and it's very nice to hear so many information. I have some a few points. So, can one treat the effect of noise as essentially controlling of chaos? Because we have several techniques to control chaos and then bring the system to order and so on. So can one treat the applying of noise basically as a method of controlling of chaos? So that is one question, one point I would like to make. And then about localized modes, intrinsic localized modes you have talked about in coupled oscillators. Can you make these modes to travel? For which do you require a critical couplings, critical noise strength, which makes these modes to travel?
Okay, so the first regarding the first question, whether we could use noise to control chaotic motions, at least in the limited set of studies that I've shown to you today, when there's a particular structure that is a stable attractor with an unstable limit cycle in our case, along with a chaotic attractor, for that structure, if there's an escape path, then it is possible to move to the periodic state from the chaotic state. So that's one possible path for it. The second one that you asked about was the localization. And I think your question was, if I read it correctly, if I heard you correctly, was can I move from different localized states? Is that correct?
Can you treat this as a traveling wave, traveling localized wave?
Traveling localized wave, okay. So in the experiments that we have all standing waves that we did. But the same setup with a little bit of modifications could allow for traveling waves. So I think consistent with dihedral symmetry, you could have traveling waves, which when the symmetry is broken, you can suppress the traveling waves. But that we've done some analysis, but we haven't done any experiments yet.
So do you expect you need some critical strength of the noise for the wave to move?
I think it would be a combination of both the temporal disorder, that is noise, along with some kind of parameter disorder, I would think.
Okay.
I think a combination of that, maybe in the parameter space, you might find a region where that can happen.
Okay.
Although right now, a number of speculation, I've not really studied in detail to answer it fully, but at least that's my thinking.
Okay. Okay. Thank you very much.
Yeah, I think there is a question in the Q&A box. Can you take a look?
Yeah. I think, well, the first one is, can you comment on the work of Rabinovich and long transient metroclinic chain subject to noise? And the second was presence of exponentially increasing timescales in Boolean networks as supertransient scaling in the presence of noise. Okay. And then there was a comment below. I don't know if they're both related. I think there's another one about noise and dynamical framework that corresponds to real and physical systems like climate, thermoacoustic systems. Okay, let me speak to Gustavo's questions first. I'm not terribly familiar with that work of Afinovich and Rabinovich on long transients. Perhaps Gustavo could say a little bit more on that.
Hello, nice to see you all. Yes, this is a work in which you have a series of saddle points, and these saddle points are in the space. And what you have is that when you introduce you establish a connection between amongst them because you introduce some noise. And so what happens is when you approach one of the saddle points, the noise makes you kind of jump over it, and then you get into the attractor. You're attracted by the other saddle points, and then you have a long chain of heteroclinic connections. And then your problem to your dynamical systems problem this is a couple of map type lab tests, many objects, and then your problem becomes the problem of seeing how these kind of serpents interact with each other. And this was developed, the formalism was developed by Valentina Fraimovich, and then Rabinovich and his groups in California implemented it in the context of neural networks. That's more or less the context of that.
Yeah. So I think so I've not personally studied that with the system that you mentioned. The closest that we have studied is the Fitzhugh-Nagamo equations. But the heteroclinic chains, I don't think we've addressed that in particular. But I think the type of noise in that case one might need is the noise that I showed you today. They're all on the right-hand side of the equation, the additive noise. In a case like what you described, I would also include noise in the coupling term. There are studies where that is also done. So perhaps that's one path towards the transient, or how to use the transients go from one attractor to another. That's one possible path. The second one that you talked about, the super transient scaling. Could you elaborate on that a little bit more?
Well, I have here the paper with me. The paper is called Super Transient Scaling in Time-Delayed Autonomous Boolean Network Motifs. And the thing is, what I from I recall, is that they include some noise that makes the characteristic timescales. Many characteristic timescales appear, and then this proliferation of timescales is what causes again this idea of having systems that don't settle down, that they live within transients. And
so
it's
we
something about in Boolean networks and things of that sort.
Okay,
and
so this
the authors are Deguis, Lohmann, Haynes, and Gauthier from Ohio. Perhaps you know him.
Yeah. I think, okay, so this one is Dan Gauthier. Okay.
Yeah.
Yeah, so this is more for computational problems. Okay. Am I correct? The Boolean networks?
Yes, these are Boolean networks, yes.
Yeah. So I think we haven't studied that in particular, but I could comment on something about the delay. So in the Kuromoto model, one could also take a delay. That could be a form of disorder, and because that will change your phase. And then in addition to that, you could look at your strength or the frequencies. You could introduce a disorder to see how they interact. That's something that can be done. And it has been shown that you could use one disorder to fight another disorder. So that's one possible comment I could make to that.
Oh, thank you so much. Beautiful talk. Thank you very much.
Thank you. So going to the next comment, Sujit, can I go to the next one?
Yes, please. Yeah, it's Chandrakala Meena.
Chandrakala Meena's comment was, our question was, what are the things we need to keep in mind before including noise in a dynamical framework that corresponds to real and physical systems like climate, thermoacoustic systems, etc.? It's an excellent question, a little bit broad for me to answer in its entirety. But in terms of noise, I think, of course, the source of noise and where it's coming from would be first starting point. And most analysis that we do are valid for the Wiener noise or something like the Gaussian distribution. Things like pink noise and others, you could use a filter equations to modify your system and still have a dynamical system that you can study. I think for the climate, I think I would study different types of noise, like what I had in one case today, with the Brownian motion, the pink noise, and the Gaussian noise. Those would all be good models to start from. The thermoacoustic systems, honestly, I've not worked with those to get and have an idea of what type of spectral distribution that they have. But if you do have the probability distribution of some type, that could also be a way to look at what type of noise model one could use. You could generalize the Gaussian noise distribution to a Levy noise type of situation and then play with the exponents to see how to change the character of your distribution. That's one possible pathway. Does that help, Chandrakala? Okay. Should I move on to the next question, next comment?
Yes, please, go ahead.
Okay. I think Chandrakala did respond. Okay. So the noise used here, all extrinsic noise applied from outside, can intrinsic noise such as population noise being such that was synchronized. Yeah, it's the source of the noise that we have used all came from the outside. Of course, you could have models like I mentioned before through the coupling could also one could bring in noise into the system too. That's a possibility too. I'm not familiar with population noise to go into more elaborate details on that one, but it is one could bring in from internal sources too. Like the pink noise in electronics comes from the electronics in the system. One, of course, one goes aerospace problems, one could also have environmental noise.
I guess the turbulence itself will give noise kind of effects.
Yeah.
Possibly, yeah. Are there more questions? Yeah, I think there's a comment now.
This one, the work might have close resemblance with anti-resonance. Is that if anti-resonance, by that they mean suppression of a resonance response? The answer, the physical manifestation is yes, but the mechanism is different. Anti-resonance is typically used in linear systems, I think, and in those cases we talk about suppressing the peak amplitude that we might get at a resonance excitation. Whereas here, the mechanism by which it suppresses is different than what one has in a linear case.
Okay. I have a question. If we had van der Waals oscillators, would you get similar results?
Yeah, you can. I think in the van der Waals oscillators, you can have limit cycles.
Yeah.
You could extrapolate now coupled van der Waals oscillators, so you could have many limit cycle solutions, and then you could try to see when the synchronization happens between them.
Or could you push them into a state of amplitude death with the help of noise, do you think?
You can. I think if it's a fixed point, so basically in that case, the fixed point typically in the van der Waals oscillator is unstable at the middle. But if there's a way to stabilize it, and then the amplitude that could correspond to moving the response to a case of a stable fixed point.
Okay, thank you. Thank you. Prof. Ambika, you have?
Yeah, very nice talk. I was just wondering, you mentioned about a partially synchronized state, somewhere in slide number 44 or something. So in that connection, I was wondering, is it possible to get some states like chimera states also by adding differential noise or something?
Yeah, you can. Actually, it's an excellent question. So in the mechanical system that we were looking at, we were always trying to get a fully synchronized state. When we do full synchronization, basically the coupling terms goes away. The system becomes coupled. So you could have, in this case that I have, when the order parameter is not 1, each state that I have is actually a partially synchronized state. It's actually chimera state.
Yeah.
More than this, I think the system, the Fitzhugh-Nagamo oscillator model that we looked at, this one here,
Yeah.
where we actually use the Levi noise to move to certain cluster states where the fields
Okay.
synchronize within the particular group, and that is possible to do. And so essentially, we're able to show that the entropy, how you can control the entropy by adding noise.
Okay.
Yeah.
Okay. Looks like we are at
Thank
the end of questions. I want to thank Bala for this wonderful talk. And we're delighted to inform you that the next webinar would feature Professor Stefan Luther from the Max Planck Institute for Dynamics and Self-Organization on January 26th, 2026. Please mark your calendars. And as we take a short break in December to celebrate Christmas and New Year, we extend you the warmest wishes to you and your loved ones for a joyous holiday season. Thank you all. And bye for the time
Okay,
being.
thank you very much. Bye.
Bye, Sujit.
Thank you.
Bye.
Bye.
Thank you.